Hello everyone, I'm Shibashish from IISc Bangalore. I'm here to talk to you about the SciAstra course on IAT and NEST. IAT is the entrance exam for IISERs and NEST is the entrance exam for NISER. You will see that the questions that come in these exams are kind of different than what you would expect in exams like JEE. Here, the questions are more catered to like test your understanding of the concept and how well you understand these things and what is the basic physics behind these things that you know of in your plus two level. It's not always about like applying formula and such. So you'll see that there's some questions which can be easily done with, like from basic formulas. So like more of it is like testing your understanding. So while solving the question paper, it's not always recommended that you go from question one, question two, and so on. You'll see that some questions are difficult and take a lot of your time. So it's better to like do the questions that you easier to you based on your understanding of the concept. And if you find something hard, it's okay to skip it and come back to it later. Because if you're stuck in one question and you spend too much time on it, it might happen that you will skip out other questions which could have given you more marks in that exam. And also it happens sometimes that if you skip a question and then come back to it after some time, you find another way of solving it and it actually appears easier. So these are some tips that will help you appear for more questions in the exam and which will help you score more marks. Now, we are going to discuss the NEST 2021 question paper today. You'll see that most questions on this chapter, like from this exam, are like general physics questions. You do not need to know any particular chapter of physics to approach these problems. They just test your general understanding of the subject. The question usually has most information given to you and just wants to know that how well you can come up with how to solve these questions based on this information that is given. So it's a general understanding of the subject. And then you'll see that many questions are from atomic physics and thermodynamics and electromagnetism. So atomic physics, modern physics, these are usually ignored subjects by students because they're taught later on, like people think they're easy and they skip it. So we'll see that here, a lot of weightage is given to these subjects. And electromagnetism is quite a complicated chapter, a vast chapter that requires a lot of understanding. And there are some questions from here, but like you'd see that with some knowledge and like some practice, we can do this. So we'll discuss some questions, and these are the types of things we'll cover in the course that we will be having. So let's go to the questions now. Let us start off with a very easy question. This question says that there are three objects rolling on an inclined plane. I'm sure that many of you would have come across this in some form or the other and like try to solve it. But you'd see that it's very easy actually. So like we have three objects: a hollow cylinder, a solid cylinder, and a solid sphere. And what matters here is like it's asking which one will reach faster and which one will reach slower. So you know that if you have an object at a height, and here it says that all have same mass. So each object at a height with some specific height, all of the three objects will have the same potential energy. And this potential energy will be converted to the kinetic energy while they're rolling down the incline. And this kinetic energy will be distributed in like two parts. One will be the translational kinetic energy and one will be the rotational kinetic energy. So you'll see that the distribution of the energy depends upon the moment of inertia of these objects. Now the moment of inertia is lowest for a solid sphere, and then for a solid cylinder, and then maximum for a hollow cylinder. So for a solid sphere, it's 2/5 mr square. For a hollow cylinder, for a solid cylinder, it's half mr square, and for a hollow cylinder, it's just mr square. So because the hollow cylinder has the largest moment of inertia, it will have the largest proportion of its energy being converted to rotational energy. And the translational kinetic energy directly correlates to the velocity. Because the translational energy is this half mv square. So higher this term, higher the velocity. And this will be higher for the object with the lowest moment of inertia, or for the solid sphere. And then second highest for the solid cylinder and lowest for the hollow cylinder. And that's why this is the order from the slowest to the fastest. The hollow cylinder will be slower than the solid cylinder, which will be slower than the solid sphere. Now let's proceed to the next question. Again, another very easy question from current electricity. The question asks that you have a wire, you're melting it and making another wire which is twice the length of the wire. Because the material is the same, the volume will be conserved. So the area times the length will be equal. Now, if the length is double, the area has to be halved. So what happens to the resistance? This is a very easy question on current electricity, which asks that you take a wire and you melt that wire and make it a wire of double the length. Now, if you're doubling the length, the area of the wire will decrease. But since it's the same material that you're using, the volume of the wire will remain constant. And the volume is given by area times the length. And this is constant. So since length is doubling, the area will become half. Now we know that the resistance is equal to rho L by A. So the length is doubling and the area is becoming half. So the resistance is increasing by a factor of 4. So the new resistance will be 4R. And because the resistance is 4R and we're seeing that we're applying the same potential difference, the current will be divided by 4 times. So the correct option is the current in the wire will be I by 4. Coming to the next question, this one seems slightly tricky. We have 3 balls which are falling down and it asks to find the height of the balls, individual balls after they collide with the ground. Now you'll see that the question says that the individual radii of the ball are much smaller than the total height h given here. This is important because this helps us to approximate that all the 3 balls m1, m2, and m3 will have the same velocity v while the m1 touches the ground. So we can make this approximation because the radii are much smaller than the height h. Now, let's assume that M1 has all 3 have a velocity of v while M1 touches the ground. And it says all these collisions between M1, the ground, M1, M2, and M3, all these collisions are elastic. So when we consider M1 with the ground, now M1 has a velocity of v. So when it rebounds with the ground, it will have an upward velocity of v. So you take the ball M1. After collision, it will have a velocity of v upwards. Now let us consider the collision between M1 and M2. Let's say this is M2. M2 has a velocity of v with respect to the ground. But if you go into the reference frame of M1, M2 will have a velocity of 2v, as M1 is also moving up with a velocity of v. So upon collision, when we are working in the reference frame of M1, we'll see that it has a velocity of 2v. So M2 will go back up with a velocity of 2v. However, if you go back to the ground reference frame again, you will see that this velocity will be 3v because as we are in the M1 reference frame, which already has a velocity of v, so we add this velocity when you're going to the ground reference frame. So M2 has a velocity of 3v upwards in ground frame. Now let's go to M3. Change it to 3v. So M2 has a velocity of 3v and M3 has a velocity of v downwards. So in the reference frame of M2, you add the 3v to the velocity of M3, and you see that with respect to M2, M3 has a velocity of 4v downwards. And so upon collision, it will have a velocity of 4v upwards. But in the ground frame, again, you add the 3v component because you're changing frames again. So it has a velocity of 7v in the ground frame upwards. Now you have the velocity. So you need to calculate the height. In kinematics, you would know that the height is given by v squared by 2g. So the height is proportional to the square of velocity. If you do not remember this formula, you can use the classical formula like s is equal to half at square and like convert the velocity time term and find the height. Otherwise, if you just know this, you can directly apply this. You see that it depends on the square of the velocity. And so the first one will be 1 and 3 square 9 and 7 square 14. So this is the correct answer. These are the ratios of which the new height of the balls will be after the collision. So this question appears tricky and it seems like, oh, maybe it will be hard to solve. But if you like analyze a little bit, you can see that it can be done very easily. Okay, this is an easy question. It's just like about calculating stuff. It gives you the energy in electron volts and the wavelengths in nanometers. So what you have to do is you have to convert it to the energy and then you find the Planck's constant. You know that E is equal to hc by lambda. Coming to this is a general question which doesn't require you knowledge of any particular subject. You see that we have given a function and you have to graph it. So the function is some exponential in the top and 1 plus some exponential divided by some factor minus some 1 divided by some factor in the bottom. So in the numerator, we have this term divided by this. This is the function that we have. Now it's given to us that ns is much larger than n. Now you see that e to the power t by tau will always be greater than 1 for any positive t, as e to the power 0 is 1. So the function is always positive. We have confirmed that. And for small values of t, you will see that this term, the ns term, is much larger than n naught. So this term will be near 0. So the numerator will be the denominator will be almost equal to 1. And the only term we have to worry about is this term. So for lower values of t, this function will be an exponential curve. So we have ruled out option 3. It can be something like this, option A, B, or D. Now let's see what happens after some time passes. Now for large enough time, you will see that e to the power t by tau will be larger than 1. So this term inside this curly brackets can be approximated to be e to the power t by tau, and the -1 term can be ignored. So our denominator becomes this. Now this term cancels out with that of the numerator. So we have 1 by 1 plus 1 by ns. And this is a constant term. So for larger values of t, our function approaches a constant term. And that is what we see in option 2. So option 2 here is the correct answer. This is an interesting question. Here you have a long wire and you have two coaxial cylinders placed around it. So you have one thinner cylinder and a broader cylinder placed at the same axis as the wire is placed. Now see that this gives us the linear charge density of the wire to be lambda and the surface charge density of the outer cylinder to be minus lambda by 2 pi r2. Now if you take the perimeter of the larger cylinder, that is 2 pi r2, which that means is the charge density or the linear charge density of the inner wire and the outer cylinder are the same and opposite in magnitude. And it asks us to find the potential for distance r, which is less than r2 and greater than r1. Now, for this part, what is the field? First, we ask like what is the? It gives us the potential at infinity is 0, but what is the potential at r equal to r2, capital R2? Here we see that the potential here will also be 0 because the field outside r2 is 0. Then how do we find that? In order to find that, let's take a Gaussian surface. So we take a cylinder with radius greater than r2, and we find the electric field at this point. Now, if the electric field exists, it will be radially outwards, as we can see from the geometry of the problem. So the field, like we only have to integrate over the curved surface area of the cylinder. However, if you take the charge inside, as we are only considering the length, some length, let's say small l, here the charge inside due to the wire will be positive, some positive quantity q, which is lambda into L, and some negative quantity minus q, which is lambda into L again, because the linear charge densities are exactly the same. So the net charge inside this Gaussian surface is 0. That's why the electric field has to be 0. As the electric field will be symmetric, so we can take it out. And this is 0. We can take the electric field out of the integral as it's symmetric everywhere. It should be symmetric everywhere on the surface. It exists because of the geometry of the problem. And we see that if we take it out, the Q is 0. So this has to be 0. Because there is no electric field, the potential at infinity will be the same as the potential up to R equal to capital R2. Now we are interested in what happens at R less than R2 but greater than R1. So we choose an appropriate Gaussian surface for that. Let's take this Gaussian surface. Here you will see the charge is equal to lambda L. Like for, let's say if this has a length L, so there's a non-negative, non-zero charge present inside this Gaussian surface. So if we do the same thing again, what we have is E into 2 pi r is lambda L by epsilon, or E is equal to lambda by 2 pi epsilon naught 1 by r. So our electric field varies as 1 by r. Now we need to find the potential at some point r. So we can integrate the electric field from r equal to r2 to r equal to r. Now what is this integral? These terms are independent of r, so we can take these out. And we just have 1 by r dr from r2 to r. And you will see that this is to integrate this, the answer is ln r. So our current, and we put in the limits in this minus sign. So putting the limits gives us lambda by 2 pi epsilon naught ln r2 pi, which is the correct answer. So coming to a question of optics, here you have a plane polarized light, which is passing through a combination of lenses and mirrors. And it asks you finally what happens to the polarization of the light after it passes through all these combinations. You would have seen that if you have unpolarized light passing it through lenses, like reflections and diffractions can make the light polarized in different directions. However, when you're dealing with polarized light, all the interactions that happen in the plane of polarization. So this plane cannot be affected, and the light output will also be in the same plane polarized light. That's why if it's all initially if it's y polarized, the final output also be y polarized. This is a straightforward question. It just tests your knowledge if you know what happens when you're dealing with polarized light. Because like we know you'd have read that, or if you have randomly oriented light without any specific polarization, lenses and mirrors can make the light polarize in different directions. This is just a test of that knowledge. Okay. Here we have a hypothetical atomic model where there are three electrons moving in the ground state of a hypothetical atom. You see that here it says that Bohr radius and the Bohr quantization rule holds for the electrons and the model. So this is a hypothetical model. This won't really help you if you only know the formula. You need to know how this formula comes and how we arrive at it. And if we're changing the conditions, like basic conditions, so how that formula will change. So we know that the Bohr radius is the radius of the electron for the hydrogen atom, or for Z equal to 1 and for a 1 electron species. However, here we are dealing with a 3 electron species, and it is given that 3 electrons are equally spaced. And here it is given that the 3 electrons are equally spaced. So what we do when we arrive at the Bohr radius of the hydrogen atom, we have to relate the centripetal force with the electrostatic force. And the electrostatic force in Bohr atom is Ze by R, Ze square by R square. However, here it will be different, as you have more than one electron, and the forces of the electron and the electron forces need to be also considered while calculating this. Let us say that this is our orbit. Now, this is our nucleus, and we have that the electrons are equally spaced. So we can draw them out like this. Now, so we need to calculate what is the distance between these 3 electrons. This is a 120 degrees. So if you draw this perpendicular, this is a 30 degrees. And this is R. Let's assume R to be the radius. So you find that this is root 3 R by 2, because cos 30 degrees is root 3 by 2. So you'll find this is root 3 R by 2. So the distance between one electron and the other electron is equal to root 3 R. This whole distance is root 3 R. Now, if you're considering this electron here, it will experience some force due to the electron here and due to the electron here. If you add these up, the net force will be in this direction. Now, this angle is 30 degrees, so this angle will also be equal to 30 degrees. So if the force due to each electron is Fe, the net force will be 2 Fe cos 30 degrees. And because you're only considering the component along this term, because the sine component will cancel out because of due to the 2 electrons, and you only have to worry about the cos component. Now let's see the net force. So the net force, this will be common. Due to the nucleus, it will be Ze square by R square, where R is the radius of this hypothetical orbit that we are going to consider. And the electrons. So the nucleus force is attractive, so let's put a negative sign here, and the electron force will be repulsive. And what is this force? This will be 2 electron charge E, so E square cos 30 divided by root 3 R whole square. because the distance is root 3, so by r square, we take the whole square. If you put the value of cos 30 is root 3 by 2. So if you have this, we take e square and r square outside. So we have z minus root 3 by 2, so 2 by 2 cancel out. So we have root 3 and a 3 here. Cancelling it out, we have 1 by root 3. So the effective nuclear attraction changes. Everything else is the same in this. Like all the same laws are valid, the quantization is valid. So what only changes is this, instead of z, you have 1 by z minus 1 by root 3. Now the Bohr radius is valid for hydrogen atom. Now if you're considering a heavier atom, but with 1 electron, what we do is we divide the Bohr radius by the atomic number of that species. So it's AB by Z. However, Z here, instead of Z, we have to use Z minus 1 by root 3 as the attractive force is also changing. So you can consider this as the apparent attraction or the apparent Z. And so we'll have a denominator as Z minus 1 by root 3. And that is the correct answer, which is given in this option. Like this was a very tricky question. It needs you to know how we arrive at the Bohr radius, how we derive this. And it tests your knowledge more than like how much you know how to apply the Bohr radius concept and the other things. So it's important to know the formula that you know and how you derive at them, like how you arrive at those formulas and what assumptions you're making while you are coming to those things. Okay, so that was a difficult question. Let's move on to a slightly easy question now. Here we have a long wire and we have rectangular coil of many turns placed next to the wire. And its question asks you about the inductance and how that depends on, let's say, the number of turns or the current in the wire. Now, how we define inductance is this. So the magnetic flux and the current are related, and this relation is given by the inductance L. So phi is the magnetic flux, I is the current. So flux and the current relation is given by this inductance term. So this inductance shouldn't depend on the current. It should depend only on the geometrical aspects of the system that we are considering. We're changing the system here, changing the orientation of the system, moving it, or like rebuilding it, like making it in a different design. Only that should affect that system. The first option says that the mutual inductance between the wire and the coil will be doubled if the current in the wire is doubled. This is wrong because the inductance is independent of the current in the wire. And the second option says the magnitude of the magnetic field due to it. So you know that the magnitude of magnetic field due to a long current carrying wire is mu naught I by 2 pi r. Here r is equal to 2 meters and I is equal to 2 amperes. So if we solve this, you will see that yes, this value does match with the magnetic field that is given. So, and the third option is correct. Here the inductance is changing. It's saying that if you're moving the wire from 2 meters to 1 meter. So what happens if we move it from 2 meters to 1 meter? You see that this is the magnetic field, right? And it's inversely proportional to r. So if you're changing the length, we're from 2 to 1, we're making r half. That's why we're doubling the magnetic field in the coil. And doubling the magnetic field doubles the flux. And since the flux gets doubled, but it's the flux due to the same current, so the inductance also has to be doubled. That's why this option is correct again. And the mutual inductance between the wire and the coil is proportional to n. This is also correct because the flux is the magnetic field per area. And if you're increasing coils, the area it increases. Like the flux will be associated with every coil. So like by having 2 coils, you're doubling the flux. By having n coils, you're making the flux n times. As now you have n loops through which the magnetic field is changing, and they will individually lead to like different EMIs being generated. Like flux will increase in that correspondence. So the flux is proportional to n. That's why the mutual inductance between the wire and the coil will be proportional to n. All right, so we discussed some questions. We'll be doing more questions like these, and we're discussing the theory that is important for these exams and will help you prepare for the same. That's all for now. Thank you.